Hi, welcome to my channel. This is a course on quantum mechanics, as maybe you people have guessed. This is a course I want aimed at high school students and undergrads and advanced high school students. I'll ensure that basically with the knowledge base of +2 physics, this course can be followed. The reference I would follow is this book by David Griffiths, Introduction to Quantum Mechanics. It's sort of a universal text that's covered in the IITs and the ISERs, as well as abroad. This is sort of a famous introductory text on quantum mechanics. This is also the book I learned from, and this is, for example, available on Amazon or Flipkart or even in your local stores. My YouTube channel, where these videos will all be uploaded quite regularly, is Ray Physics Made Let's Scary. And my email ID, where I would be okay to take questions, are ognivo.physics@gmail.com. So yeah, let's begin. So I'll start with a basic. I'll start with the standard physics that we know from school, right? The first equation that we know from school is F is equal to ma, right? This is the most basic equation that we know, where force is related to, the force is basically the derivative of the potential, the force acting on a particle, and this A is the second derivative of the trajectory that a particle, say this is a trajectory of a particle, x of t being time, and if I know this force on the left hand side, it helps me calculate the second derivative of the particle. So it tells me how if I know, for example, if I know f as a function of time, say I know what x of t is, I know this, I can solve this equation essentially. As an aside, in this course, anything that I mention with the side would be something beyond what's there immediately in the book in Griffiths. These are true statements, and these I mention so that the context becomes clearer. If something that I say in the aside section is not immediately clear, that's fine. You don't need to immediately understand everything. But these are just for your additional knowledge. So as an aside, since this is this variable, which is second derivative in t, is second derivative your solution in classical mechanics actually depends on two constants, say c1 plus c2 of t. For example, this is the solution if f of t is 0. How do I know this? Well, if I take the second derivative, I get 0. But the crucial point is it involves two undetermined constants. By undetermined, I mean it cannot be known from this equation that I wrote here. You need to give me the value of C1 and C2 from outside. The physics will not tell you. someone who's doing an experiment, or someone else has to tell me what these values are. It cannot be determined from the dynamics, from the equation itself. Okay. Um, Again, as an aside, later on you will know, or probably you will know in your courses, that these are fixed by boundary conditions. And this is crucial in physics. I don't know if you are told this in high school or in your undergrad courses. This is actually crucial. It's crucial. Boundary conditions. Good. This was basic classical mechanics, right? This is the root of your classical mechanics. So what is quantum? Where is question? Where is Mr. Quantum? Eventually, we are interested in quantum mechanics, right? That's why you are here. Okay. So, of course, it's a vast area. Quantum mechanics actually, it's all of physics, essentially. Crucially depends on, well, two legs, let's put it that way. The quantum world and general relativity. This is where famous Mr. Einstein was located. This is, well, in the early days, Niels Bohr. Who else? Well, a lot of people. Schrodinger, Max Planck, and so on and so forth. Oh. Yeah. And lots of other people. Why did I distinguish between them? You should ask. Why is it separate from this guy? Well, I drew two legs, right? This is a huge mystery in physics, okay? That the quantum world is seemingly quite distinct from the world of general relativity. So, atoms, this is where, for example, atoms are. And this is where, well, black holes are. Or galaxies, yeah. And why are they different? Well, it's a huge mystery. It's an ongoing work. Nobody knows why they are so distinct. There are, in fact, various theories that try and bring the two together. One of them is called probably the most famous of them is called string theory, which is quantum theory. There are other theories of quantum gravity, and this is also where I work. For example, if you guys are interested in this deep mystery as to why these two, why this world is so distinct from this world, a classic book that I read during my when I was in school, and which made me so interested in physics is the book by Brian Greene, The Elegant Universe. It's a magical book. Yeah, if you, again, it's available on Amazon. If you guys are interested, or if you have time, please go through it. It's something that made me decide that I want to pursue physics, for example. It was that good. Okay, so much for stories. So where does quantum mechanics start, or how is it different from, say, from this classical equation that the simple classical equation, well, Newton's equation that I wrote here. So quantum mechanics actually deals with wave functions. For if you are an high school student, maybe you are hearing this for the first time. So what are wave functions? Well, instead of, for example, having an equation like ft, say, ma, where your variables are x of t, like you have a time axis here, say you have x, you have t here, and say this was the trajectory of your particle. This is the classical picture. Quantum mechanics asks a different question. Quantum mechanics gives you an equation which is analogous to this equation. Say, for example, it's called the Schrodinger equation. What is this equation? Well, this IH cross del psi del t is equal to minus h cross by 2m del square psi del x square plus some function of x times psi, which of course is a function of x and t. So lots of new stuff, right? But in principle, it's just a different equation, right? So this is a different equation, well, analogous to this, right? In principle, but in practice quite different. So let's first define the terms. What are the terms here? So I, maybe, it's minus 1, square root of minus 1 actually. Psi is called the wave function. It's a function of, say, in one dimension. For simplicity, this is the 1D, one dimension, one space. Well, one. It's actually not one dimension. One spatial dimension. So this is called the wave function, which is the primary object of interest in quantum mechanics. What else do I have here? H bar. This is called reduced Planck's constant. Why reduced? Well, this is actually by definition h by 2 pi. Well, you know what pi is, right? 3.14. It's a constant. 14159. A constant that never ends. It's quite important to remember that. It never ends. H is called the Planck's constant. So h by 2 pi is the reduced Planck's constant. Well, the value is a little less, right? What else was there? Right. And V is some potential. Exactly analogous to, well, what you would have in classical theory. For example, let me remind you what V is in classical theory with say a spring. So we all know how the potential for a spring looks, right? It looks like a parabola. It doesn't look like a parabola, it is a parabola. So yeah, roughly this. And this and this. This is your x direction. This is your v of x. And this curve has an equation, say v of x, some constant times k square, right? So it's a confining potential. What does it mean? That this potential, what does a confining potential mean? This potential grows without bound as x tends to plus minus infinity, right? So somehow the picture you should have in mind is like a particle is sort of confined in this region. It cannot escape to infinity. It cannot escape. Cannot. Good. Oh, I think I have pressed this by mistake. Right. So at least the new players are understood, right? To briefly recap, this is square root of this is square root of minus, this guy is square root of minus 1. This is the reduced Planck's constant. Planck's constant, m is the mass, the same mass that you have here. For example, the mass of a particle. Psi is something that you would be solving for, exactly as you solve for xt here. And this psi generically is a function of x and t in one dimension, like you have a one spatial dimension. And you have the potential here, which may be 0, of course. I mean, in the simplest cases, for the free particle, it would be 0, right? So it would be 0 for a free particle. A free particle, by definition, means it's not influenced by any force, right? So the potential is 0. So the for example, the free particle Schrodinger equation would just be this much. You just have to solve this second order equation. Yeah, and we will do that. We will explicitly do that. Good. So I think I have already spent a bit in just introducing the basic equation. And this has this, by the way, I see in Griffiths that they have mentioned this value. It's not particularly important. Well, it's important for historical reasons, but it won't be important for us because we'll set it to 1 later when we actually do computations. But it's important thing is to realize, though, that this is a very, very small number in the SI units. You know what the SI units are, right? Very small number, 10 to the power minus 34. The reason it's important is it's precisely because it's such a small number that you don't see quantum effects. You don't see quantum effects in everyday life. You don't see quantum tunneling, for example, in everyday life. What do I mean by quantum tunneling? You don't walk across a wall in your everyday life. Although in the quantum world, it is allowed, and it does happen for subatomic and atomic particles, actually. It's precisely because this number is so small, the value of this h bar is so small, that the effects of quantum mechanics are not visible, for example, in your everyday life. Just like, for example, in general relativity or in relativity, for example, this is not a relativity, of course, but why not? In relativity, you'd have the speed of light, right? Which is 2.99 into 10 to the power 8 meter per second. And it's precisely because this is actually quite a big number in appropriate units that you don't feel, for example, time dilation, right? Yeah. So it's again because of these constants, the particular values, the smallness of this guy, of the Planck's constant, and the largeness, let's say, of the speed of light, that you don't feel respectively you don't see the quantum world or the relativity world visibly. So yeah. Right. So where were we? Okay, so much stories, but where were we? We wrote an equation, a God-given equation. I didn't derive it. So yeah, so you could ask me, where did this come from? Well, this is Schrodinger's equation. It was his brilliance. He came up with this equation. And the point is, the goal is, or the whole exercise is, don't worry, I'm not giving you homework right now. The whole exercise is to figure out or to solve for this x and t. This guy. Solve for the wave function. Exactly analogous thing you did actually here in classical mechanics, right? You solve the different equation, that's all. You solve the different equation, something like this. Now you're instructed to actually solve a different equation called the Schrodinger equation. It looks scary, but trust me, it's the same thing. It's exactly a second order equation, just as this one was. Okay, good. Question you should have, and this is maybe where we would stop today, is what will I do with this guy? The guy being this wave function. I mean, in the classical mechanics picture, it was quite clear, right? In the classical mechanics picture, you solve for x of t, which basically told you as a function of time where you are. This is x, this is t. So t equal to 5 seconds, say for example 0.5 second, you have a particular value of x. T equal to 0.8 second, for example, you have a particular value of x, right? So that's the whole program of classical mechanics. One of the whole programs, well, not the whole program, but one of the programs, right? Like, given a time, it should tell me, you should be able to tell me where you are, these values of x. And you can do a lot better. So if I know x of t, for example, if I know this guy, I know what x dot of t is, the derivative. And this is related to velocity, right? For example, again, very simple example. Say your x of t is, say, 5t squared plus 3t. And you can ask me what the velocity is. Well, it's simply 10t plus 3. So again, I can have a graph for your velocity. Something, it's linear, right? Starting from 3. So it should be something like this, maybe. Yeah. Okay, these graphs don't take it for like too seriously. I'm just trying to explain a point. So, oh, sorry, this is v of t. This is a profile for the velocity as well. This is v. Yeah. Good. So now the obvious question is, okay, great. I have solved for psi. Say exactly as you did here, for example. I have solved for, say, psi of x of t. I know what this guy is. You asked me to solve this equation, Schrodinger equation. What will I do with it? Well, this is where quantum mechanics comes in. Quantum mechanics actually does not ask you for trajectories of this kind. Okay? This is a deep point. In fact, in quantum mechanics, you cannot have trajectories of this point. Okay? There is something called an uncertainty principle of Heisenberg, which tells you cannot, well, unless there is an infinite lack of information about momentum, you cannot have such a curve in the quantum world. Okay? So what quantum mechanics does tell you instead is basically the probability of being between, say, x is equal to x0, or whatever. Let's make it simple. Yeah, you guys are just high school students, right? So x equal to 1 centimeter and x equal to 2 centimeter is given by, this is where psi comes in. This is why you solve psi for by this integral. X is equal to 1 to x equal to 2 centimeters dx psi x of t mod square. Okay, so let this sink in. It tells you first, what does it tell you? Again, recap. It tells you, 1, probability. It does not tell you exactly where you are. It cannot, in fact, tell you exactly where you are. Just as I had mentioned, it cannot tell you the trajectory. Okay? This is exactly what is known as quantum indeterminacy. It's not that you don't know, it's you can't know. There's a difference. Okay? So this is different from classical indeterminacy. This is quantum indeterminacy. It tells you cannot know that. Okay? Or in other words, such a fixed trajectory where you explicitly know the trajectory as a function of t is impossible in quantum mechanics. It tells you however, it does the next best thing. It tells you a probability. Okay? It tells you, for example, a probability that a particle is, say, between x equal to 1 say x equal to a rather, and x equal to b. Of course, if it's a and b, then you would have a here, you would integrate from a to b. Let's do that. From a to b. Okay? So, it tells you only probability. Again, let me reiterate that. Because it cannot tell you exactly where you are. A brief analogy. Say, okay, this is just a story, okay? This is just, just to understand. Say, your mom asked you, hey, where are you? So in classical mechanics, you'd say, I am at my friend X's house. In quantum mechanics, now you have grown a bit bigger, right? You're a lot older, so you don't want to tell your mother where exactly you are. So you do a cheeky little thing. You tell her that you are at your friend X's house with, say, half probability. Of course, we know that probability has to be less than or equal to 1. To your friend's house Y with, say, 1/3 probability. And at your friend's, say, Z with 1/6 probability. Of course, the sum has to be 1. This is 1, right? I hope this is 1. Yeah. So 3/6, 2/6, and 1/6. Yeah, it's 1. So now you are a bit older. Now you don't want to tell your mother exactly where you are. So you tell your mother that you are at friend's X house with half probability, Y's house with 1/3 probability, and Z house with 1/6 probability. So quantum mechanics actually gives you these probabilities, okay? It's crucial that you appreciate this point. It cannot tell you or tell anyone that it's not deterministic. There is a quantum indeterminacy. So generally, what it does is actually tell you these probabilities for different events to happen. Okay, these are essentially events. Like you being at your friend's house is an event. You being at someone else's house is an event. So these are all called events. So it tells you quantum mechanics tells you the probability of these events, and how are these events measured? These events measured are by evaluating this integral. You have a modulus here. This is the modulus in quantum mechanics, in complex variables. So this modulus means, for example, mod of, say, 3i is square root of 5 square plus 3 square, whatever that number is. I just made it up in my head, so I don't know what this number is. So it's modulus because typically these wave functions are complex. These ix of t are typically complex. Okay, and you have say you integrate from x equal to 8, x equal to b, suitably normalized. Of course, this gives you a probability. So you solve a Schrodinger equation to find this psi. You take its mod square and you integrate. That gives you the probability of that event to be happening. In this case, it gives you the probability of x lying between, say, the particle lying between x equal to b, x equal to a, for example. Just as an example. Okay. So to summarize, basically, this integral, to perform this integral, you need to know this, and Mr. Schrodinger tells you exactly what this is in terms of an equation. Where did I write that equation? Okay. This is that equation that the psi follows. So you solve for psi from this equation. You go to your favorite integral. And since you have all passed high school, maybe you are very good, very adept at solving these kind of, figuring out these kind of integrals, right? So yeah. So that's it for today. This is where I'll stop. Maybe we spent half an hour, maybe approximately. And I'll take it up next time. So another thing that I wanted to say is one, we will have tutorial classes as well, exactly like these lectures. Two, please subscribe so that you get to know when I am uploading next. P, so that, well, I already wrote so that we can form a community and share problems, share exercises, solve problems, etc. together. And I hope you had fun. So if you have questions, so firstly, so this is the YouTube channel. Maybe you already know because you are watching this video here. And if you guys have questions, feel free to drop those questions at my Gmail ID. I'll occasionally take a look, and I'll try and answer all of them. So this is my Gmail ID. So see you next time for the tutorials where we'll solve some problems, some easy problems, and in the next lecture. Bye. Have a good day.